Hello everyone, welcome to the next chapter. In this chapter, we will explore heat transfer analysis with a heating coil. Let us begin. We shall see the major parts of heating coil. The heating coil primarily consists of heating element. This is mostly made up of nichrome filament. Nichrome is the name of the alloy. It is made up of nickel chromium alloy. It is commonly used because it has got high resistivity. High resistivity will lead to higher resistance and thereby higher heat generation. We can see in this image, nichrome wires are sent inside this heating coil. It will be wound inside this heating coil like this. It will be having smaller diameter and larger length. We shall see why. The next part is insulating material. Insulating materials are mostly made up of magnesium oxide because it is electrically insulated and thermally conductive. It means from the nichrome wire to the outer casing, only heat will be transferred. Current will not be transferred. Therefore, it is electrically insulated and thermally conductive. And the next is the outer casing. It will be mostly made up of copper or stainless steel with chrome plating to avoid corrosion. So these are the major elements of the heating coil. Please note that the nichrome coil will be having higher length and smaller diameter inside this heating coil. If we consider a common household coil, the length will be approximately 20 meter and the diameter will be approximately 1 mm because resistance increases with respect to length and decreases with respect to diameter. Therefore, resistance is inversely proportional to area and directly proportional to length. Higher the length, higher is the resistance, and lower the area, higher will be the resistance. We can write resistance is equal to resistivity into L by A, where rho represents resistivity. This is a material property. Nichrome is having higher resistivity. That's why most of the heating coils will be having nichrome as the major heating element. Next, from this resistance, we can calculate the heat generation. Heat generation is equal to I square RT, where I is the current, R is the resistance, and T is the time. This is equal to heat energy, and the unit is joules. If you remove T, then it will become heat transfer rate or power, and the unit is watt. Therefore, effectively, higher resistance leads to higher heat generation. Okay, moving ahead, we shall do some power calculation for an instant water heater. The model is shown here. In this case, we shall directly take this model and do the meshing and analysis. We shall not create the model in design modeler. Okay. Typically, for household instant water heaters, the power rating will be approximately 10,000 watt. If it is immersion water heater or water geysers, it will be in the range of 3,000 to 4,000 watt. Okay, we shall see the other parameters. The fluid is water here. The inlet temperature of the water will be 20 degrees Celsius and the mass flow rate will be 0.1 kg per second, which will be approximately 0.1 liter per second. And the specific heat of water is 4184 joule per kg per Kelvin. So if 10 kilowatt of power is applied to this incoming water, let us calculate the exit temperature. We know that power is equal to m dot Cp into T2 minus T1, where m dot is the mass flow rate, Cp is the specific heat, and T2 is the exit temperature, and T1 is the inlet temperature. Substituting the values, we will get T2 is equal to 43.9 degrees Celsius. Approximately, the delta T will be equal to 23.9 degrees Celsius. Okay, we shall do the analysis in Ansys CFX and find out the exit temperature. Note that for this model, we will consider the heating element as copper.